Alright, so my name is Natalie Pacheco Garcia. I am doing my final project for physics for my instructor, David Fallis. I will be reading off my laptop, so that's why you will be seeing me over here. But for my final project, I'm going to be using Module 4, 5, 6, and 2 examples of the 7 as well. So for Module 4, we learned that momentum is conserved in all collisions, explosions, and events involving motion, meaning the total of momentum of a system remains constant before and after the event. Sometimes it may appear that momentum is not conserved, but that is usually because the system is being analyzed is too limited. If the system is expanded to include all interacting objects, momentum conservation still holds true. The conservation of momentum is relied heavily on the ultrasound machine when interpreting how the sound waves interact with moving particles. Momentum and energy are used in medical sonography due to their high-frequency sound waves that are used in images to capture the body. This will help with depth and resolution. There is also reflection in momentum caused by the sound waves. Due to our body having muscle and fat tissues, it causes it to reflect. For Module 5, in Module 5, we learned about Ohm's law and how it is a fundamental principle in electricity that describes the relationship between voltage, current, and resistance in an electrical circuit. While Ohm's law is not part of the core physics of ultrasound wave propagation or imaging, it is crucial to the function and design of the electrical systems inside diagnostic sonography equipment. Ultrasound machines use piezoelectric transducers to generate and receive sound waves. The transducers are driven by electrical pulses, and the generation, timing, and amplification of these pulses are governed by standard electrical principles, including Ohm's law. In medical sonography, the ultrasound machines contain crystals. These are vital since those same crystals convert electrical energy into sound waves that are converted into echoes and processed into images. We cannot forget that, like most medical devices, sonography devices also run on electricity, which is the principle of electricity and magnetism. In Module 6, we learned about light and visible light reflection and transmission. When light waves strike an object, they cause the electrons in the object's atoms to vibrate. If the light's frequency does not match the object's natural vibration frequency, the electrons vibrate only briefly and weakly, then remit the energy as a light wave. Light may not seem like it is used in medical sonography. However, it is a wave. The physics behind the reflection, refraction, scattering, interference, etc. applies to my field. It helps us understand how the light interacts with different tissues and how the ultrasound waves will behave in the body. Electromagnetic and mechanical waves share very similar wave interaction principles, especially in how waves behave when they encounter different materials. For example, in light, if light hits an opaque surface, it's reflected because the energy doesn't pass through. So that's like for reflection. If the material is transparent, the wave energy is transmitted through the material for transmission. In ultrasound, when sound waves hit a boundary between two tissues, for example, muscle and bone, part of the wave is reflected through the transducer. This reflected wave is used to create an image reflection. If two tissues have similar acoustic properties, the ultrasound wave passes through with little reflection like transmission and helps scan deeper tissues. For Module 7, which is the last module that I chose, it was vibration, sounds, and waves. This is the backbone of sonography. Medical sonography uses high-frequency sound waves to travel through the body's tissues. These sound waves allow us to take the images necessary. Vibrations produce high-frequency ultrasound waves that travel into the body. A real-life example, I'm going to be explaining the Doppler effect and how it is directly tied to momentum. In medical sonography, there is Doppler ultrasound, that is a special kind of sonography used to measure blood in blood vessels. There is an energy transfer that consists of high-frequency sound waves that hit moving red blood cells in the bloodstream. The frequency causes motion in the blood cells, causing a shift, which is called the Doppler shift. The amount of energy lost or gained in the wave tells ultrasound techs how fast the blood is flowing. This allows for detection of leaky valves or blockages. Overall, physics is very important in my field, and I'm very grateful to have learned what I have learned this semester.